Welcome back. So now let's work with SVM, but with non-linear datasets, right? So let's start by working with the synthetic data composed of the XOR gate, right? So what is the XOR gate? We have two inputs for this gate, right? It's a function. So it's a function that takes two inputs, right? We have two inputs for the XOR gate and one output. So if the input is 0 and 0, then the output is 0. If the input is 0 and 1, then the output will be 1. If the input is 1 and 0, it will be 1. And if the input is 1 and 1, then the output will be 0. So this is the XOR function or the XOR gate, right? We have four possible combinations for the very basic XOR gate. And what will happen is that the output will be 0 if we have both of the inputs are 0 or both of the inputs are 1. And the output will be 1 if one of the inputs is 1, right? So this is how the XOR gate works. Now let's generate the data. So we will use the random seed equals 0, right, to reproduce the results. And then from NumPy we have random, and from random we have randn. Okay, so this will generate 500 integers. So if we print here XOR, what you will see is that we have 500 times 2. So we have a list, okay, and this list is 500 by 2. So we have 1000 elements, right? 1000 numbers. And these 1000 numbers are inside this XOR variable, right? And after that, what we are going to do is that inside NumPy, we have a function called logical XOR, okay? So this will basically compute the truth value of x1 XOR x2. So we will give it x1 and we will give it x2. So how we are going to do this? We are going to do this very easily. So if we just write XOR all and 0, so if we print this here, you will see that we have the first column, right? We have 500 elements or 500 values, right? If we write here 1, then we will have the other 500 values, right? So if we just come here and write bigger than 0, you will see that we have true and false, right? So this will return either true or false, okay? And this will return also true and false. So we will have a list here containing 500 values, all false and true, right? All of them are false and true. And we have here 500 values, and all of these values are either true or false, right? So true is corresponding to 1 and false is corresponding to 0. And we are going to use the logical XOR to have the output just like this. So if I show you the output, if I just print y XOR, you will see that we have true and false, right? So we have true and false also, and false, we will have false if both the inputs, so this is false and this is false, or if this is true and this is true, right? And for true, it's either this is true or this is true, okay? Now, if we want to have the final output, right? So if I show you the final output, you will see that we have zeros and ones. So this function called NumPy where, right? This is basically a mapping function. So this will take the original or the input XOR, right? The y XOR, which is true and false. It will map each true to be 1 and each false to be 0, right? Or the other way around. So let's take a look to make sure. So let's take a look here. You will see that each false, right? False, false, true, true, true is now 1, 1, 0, 0, 0. So every single false value is now 0 and every single true value will be now 1, right? So if you want to have it the other way around, we will have here 1 and then here we have 0, right? So if we run this, you'll see that 0, 0, 1, 1, 1. So every single false will be 0 and every single 1 will be true, okay? So this is basically our input and output. This is the input and now this is the output, right? Now we will split the data using the shuffle arrays unison function, right? Just like before, and we are going to have 400 examples in the training and 100 examples in the testing. Okay, this data is non-linear. This XOR function is non-linear. How we know this? Let's take a look at the data. So if we look at the data right now, I will show it to you using the same code we had before, but right now we are training 4 different classifiers. The first one is linear, the second one is linear, but we have different C values, and then we are using also the polynomial and the RBF. Okay, the same everything as before. So if you see now the data, it's pretty clear that the data distribution is non-linear, right? Why we are saying this? Because we cannot have any linear curve here or any linear line here to split the data, right? We need to have something that is more complex than just a linear line. Okay, so now using a linear kernel with C equal 0.1, the SVM will fail. We cannot really find any splitter or any decision boundary, right? It will just classify everything as 0, right? So all the triangles will be misclassified, right? So if we use a linear kernel with a very, very small value for C, then the algorithm will fail, okay? Because the algorithm is trying to classify all the data points correctly, and we are going in the direction of hard margin, right? So the algorithm cannot really do anything, cannot really find a way to split the data or to find the decision boundary that satisfies the SVM conditions, so the algorithm will fail. Now, if we change the C value, so if we increase the C value a little bit, so instead of 0.1, we increase it to 10, right? As you can see, we have a decision boundary because we are going in the direction of the soft margin. So we tolerate the misclassification more and more. So we can find a decision boundary. But it's pretty clear from this decision boundary, it's not good at all, right? It's not really classifying the data correctly at all. We have a lot of misclassification here and a lot of misclassifications here, right? So linear kernel will definitely fail. So by looking at the data, you can know if we want a linear kernel or not, right? If the linear kernel will work or not. Okay, so if we have a linear dataset, the linear kernel is most probably your best choice to start with, at least. If you have a non-linear data, then the linear kernel is not going to work at all. So you don't really need to spend any time tuning for the kernels. Okay, now let's take a look at the polynomial and the RBF, right? So if we choose a polynomial with C equal 20, as you can see, we have something that is really not representing anything, right? So we have the decision boundary here, right? So the data is not really classified correctly at all. So let's ignore the polynomial kernel for now, and let's take a look at the RBF kernel. So it's clear here from the RBF kernel that this is the best possible split for the data, the best possible decision boundary for the data, right? This is the best classification we can do. This is actually the correct distribution of the data, or roughly speaking, it's the best split for the data, right? So this is classified correctly, and this is almost classified correctly, and all this is almost classified correctly. So by taking a look at this graph, it's clear that the RBF is the best choice if we have non-linear data sets. Okay, so let's take a look at the RBF with different values. So here we tried linear, polynomial, RBF. We found that we don't really have the choice even to choose the linear kernel because it will not work whatever we do. And the polynomial kernel, maybe we can try it more and more and change the hyperparameters and see what is the performance of the polynomial kernel. But as we can see, the RBF kernel is giving the best results. So we can investigate more in this part, right? We can investigate more the RBF kernel. So that's what we are going to do in the next cell. So we are trying RBF with C equal 0.5, and now we change the gamma, right? So we will try 4 different combinations for the C and for the gamma, right? So if we take a look here, as you can see, now here we have C equal 0.5 and gamma equal 0.5. And here we have C equal 5 and gamma equal 5. All of these 4 graphs are actually the same kernel, the RBF kernel. Now let's take a look at this one with this one, right? So here we have C equal 0.5 and gamma equal 0.5. Here we have C equal 0.5 and gamma equal 5, right? So we increasing the gamma, right? We are increasing the gamma. So if we increase the gamma, what will happen? Smaller gamma values make the pill-shaped curve wider. That's what we said before, right? So if we have smaller values for gamma, then the pill curve itself will be wider, so it will be smoother, right? The decision boundary will be smoother, right? That's what we are seeing here, and we tend to fit the data and then tend to underfit the data, right? But this is overfitting the data a little bit, right? Because we can have something like this or have something like this. This is not the best decision boundary, right? This is a little bit overfitting, right? This is more generalized. So decreasing the value of gamma will lead to a smoother decision boundary, right? So that's why this is better than this one, right? Now let's take a look at this graph and this graph. So we have the same value for gamma, but we are increasing the C value, right? So we have here C equal 0.5 and here we have C equal 5. So by doing so, we can see that there is not much difference, right? Maybe this is overfitting than this one, but you can check the accuracy of this one and check the accuracy of this one and see how different they are, right? Increasing C from 0.5 to 5 didn't really have that much effect, right? And of course, increasing gamma and increasing C at the same time. So if we take a look here and here, it's clear also that if we change gamma, if we increase gamma, then the decision boundary will be not that smooth, right? It will be rougher and rougher, right? So that's why this is better than this, and the best one is this one, right? So this is just exploration for the different hyperparameters we have for the SVM. We have the kernels, we have the C values, and then we have the gamma in case we are using an RBF. Okay, now in the next lesson, we will see how we can use the SVM in case of multi-class. So if we have multi-class classification problem, and in case we want to work with regression problems. So if we want to work with regression problems, how we can use the SVM and how the problem formulation will be different. So let's go to the next lesson and see all this.